10.9 Convergence of Taylor series. The outline of this video is as follows. We will begin with the formal statement of Taylor's theorem, which gives us Taylor's formula. This formula introduces the concept of a remainder term, which is the key to understanding when a Taylor series actually converges to the function it represents. Next, we will introduce the remainder estimation theorem, a powerful tool that provides a bound on this remainder. With this theorem in hand, we will see how to perform mathematical operations on known Taylor series to create new ones. Finally, we will apply these concepts to the practical task of estimating the error that occurs when we use a finite polynomial to approximate a function. This slide presents the formal statement of Taylor's theorem. This powerful theorem allows us to approximate a well-behaved function with a polynomial and, most importantly, gives us an exact expression for the error in that approximation. The theorem requires that the function f and its first n derivatives are continuous on a closed interval from a to b. It states that the value of the function at b, f of b, is equal to a polynomial of degree n plus a specific remainder term. This polynomial part is constructed using the derivatives of the function evaluated at the starting point, a. The final term is the remainder, which represents the error. Notice its structure. It looks like the next term in the series, but the derivative is evaluated at some unknown point c, which lies somewhere between a and b. As the slide notes, this is a generalization of the mean value theorem. If you consider the case where n equals 0, the formula simplifies to f of b equals f of a plus f prime of c times the quantity b minus a, which is precisely the mean value theorem. The essential takeaway here is that Taylor's theorem provides an explicit formula for the error term when approximating a function with its Taylor polynomial. We can now state Taylor's theorem in a more practical form, which is essential for understanding the accuracy of our polynomial approximations. This version, known as Taylor's formula, says that a function f of x is equal to its nth degree Taylor polynomial p sub n of x plus a remainder term r sub n of x. The polynomial part is our approximation, while the remainder represents the error of that approximation. The formula for this remainder term is what makes this so powerful. It states that r sub n of x is equal to the quantity f to the n plus 1 derivative, evaluated at some number c, divided by the quantity n plus 1 factorial, all multiplied by the quantity x minus a, raised to the power of n plus 1. The key detail is that this number c is some value between a and x. While we do not know c exactly, this formula gives us a way to analyze and bound the error. This means we can express any well-behaved function as its Taylor polynomial plus a precise, though not always easy to calculate, error term. We have seen that a function can be approximated by a finite Taylor polynomial. The crucial question now is, when does the infinite Taylor series perfectly represent the function itself? The answer lies entirely with the behavior of the remainder terms. Recall that for any number of terms, n, the function f of x is exactly equal to the nth degree Taylor polynomial plus the remainder term r sub n of x. For the infinite series to converge to the function, this leftover piece, the remainder, must shrink to 0 as we add more and more terms. This provides a clear and essential condition for convergence. The limit of the remainder term, r sub n of x, must be 0 as n approaches infinity. If this condition holds for all x values in a given interval, then we can confidently state that the function is equal to its Taylor series representation on that interval. Therefore, to prove a function equals its Taylor series, we must show that its remainder term vanishes. Now we will show that the Taylor series for e to the power of x converges to the function itself for all values of x. This requires proving that the remainder term, r sub n of x, goes to 0 as n approaches infinity. The remainder is given by the formula e to the power of c divided by n plus 1 factorial times x to the power of n plus 1, where c is some number between 0 and x. To analyze this, we find an upper bound for its absolute value by considering two cases for x. First, if x is less than or equal to 0, then c must also be less than or equal to 0. This means e to the power of c is at most 1, so the remainder's magnitude is less than or equal to the absolute value of x to the power of n plus 1 divided by n plus 1 factorial. Second, if x is positive, then c is also positive, so e to the power of c is less than e to the power of x. This gives a similar bound, just with an extra factor of e to the power x. We know that the limit of the fraction x to the power of n plus 1 over n plus 1 factorial is 0 for any x. Since our remainder is always smaller than a term that goes to 0, the remainder itself must also go to 0. Therefore, the Taylor series for e to the power of x converges to e to the power of x for all real numbers. This slide introduces the remainder estimation theorem, a crucial tool for proving that a Taylor series converges to its original function. The theorem operates on a simple condition. If you can find a positive constant, m, that is an upper bound for the absolute value of the n plus 1 th derivative of the function over the interval from a to x, then you can bound the errors. The theorem states that the absolute value of the remainder term, r sub n of x, is less than or equal to m times the absolute value of the quantity, x minus a, raised to the n plus 1 power, all divided by n plus 1 factorial. This is incredibly useful for functions with bounded derivatives, like sine and cosine, where we can always set m equal to 1. The main takeaway is this. If this upper bound on the error goes to 0 as n goes to infinity, then the remainder itself must go to 0, proving the series converges to the function. We will now use the remainder estimation theorem to prove that the Maclaurin series for sine converges to the sine function for all values of x. The key insight comes from the derivatives of sine. Every derivative of sine of x is either plus or minus sine of x or plus or minus cosine of x. Because the absolute value of sine and cosine never exceeds 1, the absolute value of any derivative of the sine function is also always less than or equal to 1. This allows us to set the bounding constant, m equal to 1, in our theorem. When we apply the estimation theorem to the remainder term, r sub 2k plus 1 of x, we find that its absolute value is less than or equal to the absolute value of x to the power of 2k plus 2, all divided by the quantity 2k plus 2 factorial. For any fixed x, this expression goes to 0 as k goes to infinity, because the factorial in the denominator grows much faster than the power in the numerator. Since the remainder vanishes, the infinite series for sine converges exactly to the sine function for all real numbers. We can now use the same approach to show that the Maclaurin series for cosine x also converges for all real numbers. Just like the sine function, all derivatives of cosine x are bounded in absolute value by 1. This allows us to, again, use the remainder estimation theorem with the constant m set to 1. For the cosine series, which contains only the even-powered terms, we look at the remainder term r sub 2k of x. The theorem tells us that the absolute value of this remainder is less than or equal to the absolute value of x raised to the power of 2k plus 1, all divided by the quantity 2k plus 1 factorial. As we established previously, this expression goes to 0 as k approaches infinity, regardless of the value of x. This means the remainder vanishes, and the series converges to the function itself. Therefore, the Maclaurin series for cosine x is valid for every real number x. Let us now look at another example of combining series, this time using multiplications. We will find the first few terms for the product of e to the power of x and the cosine of x by multiplying their known series expansions. First, we write out the Maclaurin series for each function. For e to the x, we have 1 plus x squared over 2, and so on. For cosine of x, we have 1 minus x squared over 2 plus x to the 4th over 24, and so on. To find the series for the product, we multiply these two series together, just as we would multiply two long polynomials. We systematically distribute each term from the first series across the terms of the second. For example, we multiply the entire cosine series by 1, then by x squared over 2, being careful to only keep terms up to the desired order. The final step is to collect all the terms with the same power of x. After combining everything, we find the resulting series is 1 plus x minus x cubed over 3, and so on. This example shows that multiplying known Taylor series is a valid and often simpler way to find the series for a product of functions. Besides algebraic operations, we can also use substitution to create new Taylor series from known ones, which is often much easier than starting from the definition. Let us find the series for the cosine of 2x. We start with the standard Maclaurin series for cosine of x, which we derived earlier. The key idea is to replace every single x in that original series with the quantity 2x. The first term, 1, is unchanged. The second term, which was minus x squared over 2 factorial, now becomes minus the quantity 2x squared over 2 factorial. Similarly, the third term becomes the quantity 2x to the power of 4 over 4 factorial, and so on. Notice that the powers apply to the entire term 2x, not just the x. After distributing the exponents, the term with x squared gets a factor of 2 squared, or 4, and the term with x to the 4th gets a factor of 2 to the 4th, or 16. This substitution method is a powerful and efficient tool for expanding our library of known series. Let us apply the alternating series estimation theorem to a practical problem. Finding the range of x values where we can confidently approximate the sign of x. Our goal is to find when we can replace the sign function with its third-degree polynomial, x minus the quantity x cubed over 6, and have an error no greater than 3 times 10 to the power of negative 4. Since the Taylor series for sine is an alternating series, the theorem tells us the error is bounded by the absolute value of the first term we omitted. That term is x to the 5th power divided by 5 factorial, or 120. We can now set up an inequality where this maximum possible error is less than or equal to our desired tolerance. As shown, we require the absolute value of x to the 5th power over 120 to be less than or equal to 3 times 10 to the negative 4. Solving for x, we multiply by 120 and then take the 5th root of both sides. The result is that the absolute value of x must be less than or equal to approximately 0.514. This means for any x in the interval from negative 0.514 to positive 0.514, our cubic approximation is accurate to within the specified tolerance. This slide presents a graph that visually demonstrates how Taylor polynomials approximate the sine function. The main curve is the graph of y equals sine of x. The other curves are the Taylor polynomials of increasing order. starting with P1, then P3, P5, and so on. Notice that as we include more terms and use higher order polynomials, the approximation gets significantly better. Specifically, the graph of the polynomial hugs the true sine curve more closely and over a wider range of x values. For instance, look at the curve for P3. As we discussed when analyzing the error, this polynomial provides an excellent approximation for sine of x on the interval from -1 to 1. This graph confirms our calculations and provides strong intuition for the power of Taylor series. This slide outlines the clever strategy used to prove Taylor's theorem and find the exact formula for the remainder term. The entire proof hinges on a repeated application of Rolle's theorem. First, we define a special helper function, capital F of x. This function represents the total error, which is the difference between the original function f of x and its Taylor polynomial, plus an extra term involving a constant, k. Second, we choose the value of k very strategically, ensuring that this error function f is 0 at both x equals a and x equals b. Since the function starts and ends at the same value, Rolle's theorem tells us its derivative must be 0 at some point in between. Third, we apply this logic repeatedly. We apply Rolle's theorem to f, then to its derivative, and so on, for a total of n plus 1 times. This guarantees the existence of a number c between a and b, where the n plus first derivative of f is exactly 0. Finally, we calculate this n plus first derivative. The expression simplifies to relate the derivative of f to our constant, k. Solving this equation for k gives us the precise formula for the remainder term. In short, the proof constructs a function whose properties force the remainder formula to appear. Let us pause to summarize the central results we have established regarding Taylor series. Taylor's theorem tells us that any suitable function, f of x, can be expressed as the sum of its nth degree Taylor polynomial, p sub n of x, and a corresponding remainder term, r sub n of x. The polynomial is our approximation, and the remainder is the error. The crucial question is when the infinite series is a perfect representation of the function. This happens precisely when the error term disappears as we add infinitely many terms. For the Taylor series to converge to f of x, the limit of the remainder, r sub n of x, must be 0 as n approaches infinity. Using this condition, we have proven a vital result for three fundamental functions: the Taylor series for the exponential e to the x, as well as for sine of x and cosine of x, all converge to their functions for all real values of x. The key takeaway is that the remainder term must go to 0 for a Taylor series to equal its function. Let us pause here and work through a couple of questions to solidify our understanding of Taylor series convergence and manipulations. The first question asks you to prove that the Maclaurin series for cosine of x converges for all values of x. This proof closely follows the one we just saw for the sine function. It also asks for the value of m, used in the remainder estimation theorem. To find m, consider the derivatives of cosine of x and determine the maximum possible value their absolute value can take. The second question is an exercise in building a new series from a known one. Start with the Maclaurin series for sine of u. Your first step is to substitute u equals x squared into that series. After making the substitution, you will then divide the entire resulting series by x squared. Be careful with your exponent rules. Please take a moment to pause the video and work through these two problems before continuing.